Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, lesson 35. Are all parabolas similar? Okay, exercise 1 through 8. See if you can do these on your own. Pause the video, come back and see how you did. So it says write equations for two parabolas that are congruent to the parabola given by y equals x squared. Okay, so y equals x squared. Let me just explain this a little bit. So if we have y equals ax squared plus bx plus c. All right, that's a quadratic equation in standard form. You can also write it this way. Y equals x minus h squared plus k. This term right here tells us whether it opens up or down. Positive, negative. Okay? The constant is your y-intercept. So if I don't have a middle term, which makes different changes to it we'll get to later, but this term here, if I have a parabola and I change this number to a positive, like instead of 0, if I change it to 1, 2, or 3, it's going to move the parabola up. If I change it to a negative, it's going to move the parabola down. So if I just add a constant onto the end, that's a vertical shift. If I change what's in the parentheses here and it's positive, it's going to move it left. If it's negative, it's going to move it right. So that's a horizontal shift. If you change both, it's a vertical and horizontal shift. Okay. So there it is for starters. So if I want to write, and this is called the parent function. This is the most basic because this is y equals 1x squared plus 0x plus 0. So we have the multiplicative identity and the additive identity giving us the parent function. Okay? So that's the most basic. And I make any changes to that, it's going to shift it up, down, left, right, or we can change how quickly it grows and that kind of thing, which is the linear term is going to change. So if we just want to write two equations that are congruent, we just want to shift it. We do not want to change its shape. We don't want it to increase slower or flatten it out. We just want to move it up, down, left, or right. Okay, so with all that being said now, if I just want to move it, I don't know, let's say up or down 3, that'd be y equals x squared minus 3. Okay, if I want to move it left or right, then I could write y equals x. And if I move it right 2, then it'd be minus 2 squared. Okay, so there's two equations, shifted down 3, shifted right 2. Now it says to sketch the graph of y equals x squared and the two parabolas you created on the same coordinate axis. So if I now graph these, let me show you what that would look like. Okay, so here are those three functions. The blue one is the parent function coming down, touching at the origin and going back up. The red one, x squared minus 3, took that same blue one and just moved it down 3 units. So if I shifted this up 3, it'd sit right on top of the blue and it'd be identical. We then took the green one and shifted it right 2. So then if I move this green one back left 2, it would be identical to the blue one. So it's just shifted to the right 2. Okay, so there's the 3 equations on the same coordinate plane. Number 3 says to write the equation of two parabolas that are not congruent to y equals x squared and explain how you determined your equation. Okay, so from lesson 34, lesson 34, we learned that the leading coefficient is 1 over 2p, okay? So if we have the function y equals 1 over 2p times x squared, and let's not worry about shifting right, left, up, or down. We're just taking that parent function and making it not congruent to the parent, okay? And in order to do that, we can change a, okay? So if p in this case was a half, then that'd be y equals x squared, because 1 over 2 times a half is 2 times a half is 1, 1 over 1 is 1, we just get x squared. So when p equals 1/2, we get the parent function. So change p, and if we change p to, I don't know, let's see, a quarter. Okay, if I change p to a quarter, then we get y equals 1 over 2 times a quarter x squared. Well, 2 times a quarter is a half, and 1 divided by a half is 2, so that would equal y equals 2x squared. Okay, so obviously the p is not the same as the parent function, which is 1/2. Change that to a quarter, and we get y equals 2x squared. Okay, the other way we could do this is just to make p equal to 1. So if I change that now, and let's change the colors of this, by the way. Okay, so now if I take that and I take y equals 1 over 2, remember the parent function is a half, 1/2 x squared. And I want to change this half to change the function. Then I'm going to say, well, let's change that to y equals 1 over 2 times, let's change the half to 1 x squared. Well, that's going to give us, actually I wanted to do this in red. Y equals 1 over 2 times 1 x squared. So I changed my p from a half to 1. That would give me y equals 1/2 x squared. Okay, so these two functions are no longer congruent because my p changed. And what is p? Well, p is the distance from the focus to the parabola and the distance from the parabola to the directrix. Okay, so now it says, write the equation of two parabolas that are not congruent. Explain how you determined your equations. So that's how you would explain it. You would change the value of p. That would then change the distance from the directrix and the focus, and thus changing the rate at which the function increases. Okay, page 2 brings us to number 4. And it says to sketch the graph of the parent function y equals x squared and the two non-congruent parabolas you created on the same coordinate axes. And I brought those equations over, y equals 2x squared and y equals 1/2 x squared, where a is different now because we changed the value of p. Okay, so the parent function has, think of it as y equals x squared plus 0, and these are plus 0 and plus 0, and the constant is our y-intercept, and that just happens to be our vertex. So these parabolas all come down to a minimum value at the same location, which is the origin. So the graph of them looks like this. So if I bring this in and let me just drop it here, this is what the three would look like. So the parent function is in blue, and the green one, 2x squared, is narrower because it's getting bigger faster. And then think of y equals 1/2 x squared as getting wider because it takes it longer to get bigger because of that 1/2 value. So there are three parabolas that are not congruent, obviously, because they share the same vertex. All right. Different foci and different directrices. Anyway, number 5. What does it mean for two triangles to be similar? Okay, well, for two triangles to be similar, we need the three vertices congruent, the three angles are congruent, and the three sides, the three corresponding sides, have to be proportional. That is the definition of similarity. So how do we use geometric transformations to determine if two triangles are similar? Well, we rotate them and we shift them and we dilate them to see if they would land on top of the original. So is the image identical to the pre-image after transformations? Okay, so two triangles are similar if we can transform one onto the other by a sequence of rotations, reflections, translations, and dilations. There you have it. Number 6, what would it mean for two parabolas to be similar? How could we use geometric transformations to determine if two parabolas are similar? Okay, well, same thing. We can rotate them so that the directrices are parallel. We can then move them so that the foci are on the same vertical y axis, if you will, the y value. And then we can dilate and adjust them so that they land on the parent function or the original. Okay, so the answer is basically the same as number 5. Two parabolas should be similar if we can transform one onto the other by a sequence of rotations, reflections, translations, and dilations. Number 7 says to use your work in exercises 1 through 6 to make a conjecture. Are all parabolas similar? Explain your reasoning. Okay, so it seems that any pair of parabolas should be similar because we can line up the vertices through a sequence of rotations, reflections, and translations. Then we would be able to dilate the width of one parabola to match the other by dilating so that the directrix of one would land right on top of the directrix of the other. Okay, page 3 brings us to problem number 8. The parabola at the right is the graph of which equation? So they want us to come up with an equation for this, but the nice thing about this page, so I am going to put a big star on this page. Okay, do they have the star symbol? You betcha, right here. How do I do that? Boom. All right, this is a really important page right here. So I'll put that right there. The reason is whenever we work problems, there are steps to answer these problems, and the steps work for any scenario. So long as we're given a focus and a directrix, we can find the equation of a parabola. So it says A, label a point XY on the graph of P. Okay, so it just says to label any point. It doesn't matter where. I could put it here, and that is the point X comma Y, and it's on the parabola P. B says, what does the definition of a parabola tell us about the distance between the point XY and the focus and XY and the directrix? Okay, so if I just now took the time here to just show you, let's do it in green and thin. So if I drew a line from here to here, a segment, and a segment perpendicular to there, those two distances are equal. Okay, so it says, what does the definition of the parabola tell us? It tells us that they are equal. So let me just bring that in as vocabulary or in verbiage. Okay, so we're going to let this point XY be any point on the graph of P. It doesn't matter where I put it. I decided to put it here. It doesn't matter. Then the distances are equal because the point, or P equals the set of all points X comma Y such that the points X comma Y is equidistant from F, the focal point, and L, the directrix. Okay, so part C, that just explains why we can do this. So the steps really begin right here. Create an equation that relates these two distances and solve this equation for X. All right, so the first thing we do, I just call it, if this is the point A, let's call it A. I'll put an A right here. Okay, That's the point A. So the distance from here to here is, it's a segment FA, and we could call this F prime. So to start an equation, all I would say is FA prime has to equal FA. Okay. Well, what is FA prime? Or F, not A prime. I put the prime in the wrong place. It's F prime A. So F prime A is right here. Well, what's the distance formula? It's x2, which is x, minus x1, which is 2. So it's x minus a negative 2, or x plus 2. Okay, it's horizontal, so there is no y difference. y2 is y minus some y that's equal is going to give us 0. So that goes away, and we just get x plus 2. Now we do the distance formula because we have a diagonal, and it is going to be, and the focal point is, let me just put that in black here. The focal point is the point 2, 0. So I'll put that up here, 2, 0. All right, that just makes it easier down here. So it's x2 minus x1 squared plus y2, which is y, minus y1 squared, which is 0. Okay, so there it is. I want to get rid of that square root symbol, so I square both sides. When I square this, I'm going to get x squared plus 4x plus 4 equals x minus 2 quantity squared plus y squared. Okay, so it's gotten simpler already. And now I'm going to do this part right here. So I'm going to leave the left alone for now. X squared plus 4x plus 4 equals, and now I'm going to multiply this times itself. That will give me x squared minus 4x plus 4 plus y squared. All right, so things are going to happen now. We have a positive x squared here, a positive x squared here. They cancel. And I have a plus 4 here. I have a plus 4 here. They cancel. And then I'm going to add 4x over to this side, giving me 8x equals, and y squared is over here. Divide both sides by 8, and I get x equals 1/8 y squared. So there is the equation solve for x. Okay, so here's the equation that relates the two, and then solving for x is what I did after. So part D, this is part C and D right here. E says to find 2 points on the parabola P and show that they satisfy the equations found in part D. So let me switch to purple. I like to pick points that are right on the corner of a grid, which means that x and y are integers. And so if I pick this point right here, that is the point 2, 4. And if I pick this point down here, that is the point 2, -4. Okay, I could also pick this point, which is the origin 0, 0. Okay, so it says find 2 points and show that they satisfy. So we're going to use this equation, x equals 1/8 y squared. So I'm going to put x in, I'll use this one first, 2, 4. So x is 2 equals 1/8, and then 4 squared. So 2 equals 1/8 times 16. Well, 1/8 times 16 is 2. So they satisfy. Okay, I could also have used the point 2, -4. So x is 2 equals 1/8 times -4 squared. 2 equals 1/8 times -4 squared is positive 16 again. And 1/8 of 16 is 2, and they check. I also could have used 0. It would have been 0 equals 1/8 times 0 squared, which is 0. 1/8 times 0 is 0, so 0 equals 0. Okay, so next is the discussion. Do you think that all parabolas are similar? Explain why you think so. Okay, so the answer to that is yes, because they all have the same basic shape. We can rotate them, we can shift them, and we can adjust the p in our leading coefficient to get them to be to land on the same location. Okay, so we can do translations and dilations to get them to be equal, so they are similar. Okay, page 4. What would we do to show that two parabolas are similar, and how might you show this? Okay, since every parabola can be transformed into a congruent parabola by applying one or more rigid transformations, perhaps similar parabolas can be created by applying a dilation, which is a non-rigid transformation. All right, exercise 9 through 12. Use the graphs below to answer exercises 9 and 10. Pause the video, see if you can do this, come back and see how you did. Okay, here we go. So we have y equals f of x, the blue, here and here. Then we have a red function as well. 9 says, suppose the unnamed red graph on the left coordinate plane is the graph of a function g. Describe g as a vertical scaling of the graph of y equals f of x. That is, find a value of k so that g of x equals k times f of x. What is the value of k? Explain how you determined your answer. Okay, so here's what we're going to do here. I'm going to just look at values on the graph. So as you can see, they share the origin 0, 0 right here. Okay, but then if I look at the y value when x is 1, the y value on the blue one is 1, the y value on the red one is 2. Okay, right there. If I go over to 2 on the x-axis, the y value on the blue is 4 and the y value on the red is 8. So what did I have to do to 1 to get 2? And what do I have to do to 4 to get 8? Well, we multiply by 2. So that would say that if we take that function g of x, the red one, that has to equal 2 times f of x. Okay, and my explanation is in what I just said there, so I'm not going to write anything, but that's what you would say. Number 10, we're going to do it again. Suppose the unnamed red graph on the right coordinate plane is the graph of function h. Describe h as a vertical scaling of the graph of y equals f of x. That is, find the value of k so that h of x equals k times f of x. Explain how you determined your answer. So we're looking for the function h of x to equal some constant scale factor k times the function f of x. So again, if I go to 1, I have to go up to 1, and that's right there. I go over 1, it looks like a half, but I don't like saying it looks like or is approximately. I like to use integers, so let's keep going. When x is 2, on the blue function, the f of x, y is 4. On the red one, when x is 2, y is 2. Okay, so on the same y value, or same x value, y was 4 and then y is 2. Y looked like 2 and 1/2. Go one more to 3, and I'm at 8. No, it's 9. And if I'm at 3, I come up, I look like I'm at 4.5. Okay, so it looks like it's a scale of a 1/2. So I'd call k 1/2 f of x. Okay. And the explanation is just explaining that picking an x value, the y values of the blue one equaled 1/2, or 2, it was, the red one was 1/2 of the blue. Okay, page 5 brings us to exercise 11 and 12. And it says to use the graphs below to answer these exercises. Suppose the unnamed function graphed in red on the left coordinate plane is g. So the first thing I want to do is label that. So let's do that. So this is y equals g of x. Describe g as a horizontal. Okay, be careful here. They want a horizontal scaling this time. So we're taking y equals f of x and scaling it horizontally. So we then would want to take points that have the same y value and how much did x change. So here's a point right here that is 1, 1. And then on the other graph is right here, and that is the point 2, 1. If I find another one, it's right here. This is the point 2, 4. And over here is the point 4, 4. So what did we do to x in this case since it's horizontal? Well, it was doubled. Okay, so now we're going to answer the question. So we are going to say that we want to describe g of x. Okay, so we're going to say g of x equals, now since it's horizontal, we're going to be inside the parentheses. So we're going to say f of, and what did we do to x? Okay, so going from here to here was 2 to 4. All right, so that is 2 over 4. So we're going from 2 to 4. So think of that as 2 to 4, like so, and that reduces to 1/2. So it would be f of g of x equals f of 1/2 x. Okay. All right, so next one, do the same thing on the other. So now it says, suppose the unnamed function graphed in red on the right is h of x. So this is h of x. Again, be careful, we're doing horizontal scaling. And we're going to pick values now horizontally. So right here is the point 1, 4. 1, 4. Right here is the point 2, 4. And then if I come up here, are there any others? Let me look. Okay, so in this case, actually I should have this over here. In this case over here, we're going from the blue parent to the red image. So we're going from from 2 to 1. So this is going from 2 to 1. This distance is 2, this distance is 1. It's 2 to 1. So I would say, it's not g, it's h. H of x equals f of 2x. Okay, and that is a horizontal scaling. Okay, this is page 6, but before I go any further, let's go back for a second. Page 5 at the bottom, I forgot to say that there's a definition there, and it says a dilation at the origin d sub k is a horizontal scaling by a factor of k greater than 0 or positive, followed by a vertical scaling by the same factor k. In other words, this dilation of the graph y equals f of x is the graph of the equation y equals some constant k times f of 1 over k x. So there's the definition of the horizontal scaling, a dilation at the origin. So now page 6, let's get to the example dilation at the origin. So now we have the parent function, let f of x equal x squared and let k equal 2. Write a formula for the function g that results from the dilation f at the origin by a factor of 1/2. Okay, so we're going to get a function g of x, says right there g, so I'm going to write g of x equals, and they want k to equal 2. So that's going to go out in front of the f. Okay, and then we're dilating f at the origin. So this goes inside. So dilating f at the origin by a factor of 1/2 would be this. Okay. But since f of x equals x squared, the new function will have the equation g of x equals 2 times, now f of x is x squared, So 2 times 1/2 x squared. So we're going to take f of 1/2 x squared, 1/2 x quantity squared. Okay, so f of x is x squared. F of 1/2 x would be the 1/2 x squared factored by that k equals 2. And then we simplify this. So therefore, g of x is going to equal 2 times. And if I distribute this, I get rid of the parentheses, by the way, it's going to be 2 times 1/4 x squared, distributing this 2 here and here. So then that will result in g of x equals 2 times 1/4 is 1/2 x squared. All right, so now it says, what would the result be for k equals 3, 4, or 5? And what about k equals 1/2? Okay, so let's do these. So for 4, k equals 3, comma, g of x is going to equal. I'm trying to think if I should cut corners here or not. Let's just try to do it without. So it would be k equals 3. That would be 3 times f of okay, so here's what we would get. G of x equals 3 times f of 1/3 x. And since f of x is x squared, this would then become g of x equals 3 times 1/3 x quantity squared. And that would simplify to 3 times 1/9 x squared. And then I would multiply that by 3 to get 1/3 x squared. Okay, now for k equals 4, we would get g of x equals 4 times f of 1/4 x. My parentheses in the wrong place. Same with here. That should be here, not here. Anyhow, g of x equals 4, and f of x is x squared, and this is going to become 1/4 x quantity squared. So g of x is going to equal 4 times, well, 1/4 squared is 1/16 x squared. And then when I multiply that by 4, I'm going to get 1/4 x squared. So you see a pattern here. When k is 3, we're getting 1/3 x squared. When k was 4, we're getting 1/4 x squared. So that should mean that for k equals 5, g of x is going to equal 1/5 x squared. Okay, but then it says, but what about k equals 1/2? So for k equals 1/2, then we would get g of x equals 1/2 f of 2x. Okay, because 1/2 is 2. 1 divided by 1/2 is 2, so that'd be 2x. So then we get g of x equals 1/2 quantity 2x squared. That will give me g of x equals 1/2 times 4x squared, distributing this. Okay, and then multiply by 1/2, and we get g of x equals 2x squared. Okay, so that's what happens with those k's. Okay, page 7 brings us to the end of lesson 35 and thus the end of module 1. Review the lesson summary. Go to your problem set.